Hello and welcome back. In example 3, we're asked to find the Maclaurin series for sine x using the definition of the Maclaurin series. So here, again, we're going back to the definition where we need to find the nth derivative of a function, and because it's a Maclaurin series, we're going to plug in a center of 0. So let's figure out what the derivatives of sine x are. Here, sine x, by the way, is our function. This is f of x equals sine x. Let me write that out. F of x is sine x. So we're going to get the first derivative of sine, that would be cosine. Let's keep getting some derivatives. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Derivative of negative cosine is sine, which kind of brings us back to our original function. Let's go one more though. Derivative of sine, back to cosine. Okay, so those are the derivatives. Now we're going to be interested in what happens when you plug 0 into those derivatives, so let's do that off to the right. F of 0, use a different color for these. F of 0 equals sine 0, which is 0. F prime of 0 is cosine 0, which is 1. Second derivative at 0, just going to think there, that's going to be back to 0. The third derivative at 0 is negative 1. The fourth derivative at 0 is back to 0. Seems like every other one is going to be 0, because every other one is a sine. Alright, so there we have the coefficients. It looks like it goes 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. Now, when those coefficients are equal to 0, that means the term, those corresponding terms, are going to be 0, because you're going to have this number right here divided by n factorial times x to the n, whatever that is. And so if any one of those is 0, well, I guess it would have to be just the function, or the derivative at 0. If that's 0, then that term is going to disappear. But let's go ahead and write out what the general expansion would look like for a Maclaurin series. That would look like this. This is the definition of the Maclaurin series. So, and what we'll do is we'll write out an expanded version of this. This will look like f of 0 plus f prime of 0 over 1 factorial x plus second derivative at 0 over 2 factorial x squared. And we'll go out to the fourth derivative. Remember that there's more after that. Okay, let's plug in what we know. Well, f of 0 is 0, and we know that much for sure. F prime of 0 is 1, so 1 divided by 1 factorial, well, that would be 1. I'm going to go ahead and leave the factorials in there though, just to see what the pattern is. So we have plus, I'll write the x on the top though, so x over 1 factorial. Really the 1 and negative 1 and the 1 and negative 1 is going to do like an alternating sign. It's going to be changing the sign in front of each of those terms. Now the next term is going to be 0. Every other term is going to be 0. The ones it looks like with the even derivatives will be 0. And then, so that here we're on the third derivative at 0. That's going to be negative 1, so minus x cubed over 3 factorial plus 0. Plus, and then we're going to have x to the 5th over 5 factorial. So x to the 5th is 1, so that's positive, over 5 factorial, and then you have x to the 5th, which you can write on the top, and so on. So we're going to have the next one will be a 0 just by the pattern. Then we're going to have a minus x to the 7 over 7 factorial plus dot 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 dot. Okay. So what we can do is then try to think of a pattern here. So it looks like there's a pattern of odd exponents. This is where taking a series or a sequence or a series and trying to look at the pattern of its terms really comes in handy. So here we have a pattern that goes 1, 3, 5, 7. So we're increasing by 2s, it looks like, which means we're going to have something like this. We're going to have, well, first off, there's an alternating part that goes positive, negative, positive, negative. So that we get by a -1 to the n, or something like that. Let's make sure it starts off at the right place first. So when n equals 0, we're going to have -1 to the 0, which is positive. And that first term there, the first non-zero term, is going to be a positive. So that checks out. And then when n equals 1, we'll have -1 to the 1, which is negative, and that next term is negative. So we're going to consider this x over 1 factorial to be the n equals 0 term, and then the negative x to the third over 3 factorial, that's the n equals 1 term, and so on. All right, so now we're going to have x to the power of an odd number. So we're going to have to do something like 2n, because the 2n is what increases the numbers on the top by 2, and we're also going to have the same thing happening on the bottom, so whatever the exponents are, the factorials on the bottom will follow. Now if we just set it at 2n, we would have n equals 0 would give you 2 times 0, which is 0, but we want a 1 up there, so we're going to add 1. Let's see if that matches. When n equals 0, you get an exponent of 1, which is good. The next n value, n equals 1, will give you 2 times 1 plus 1, which is 3, and that's exactly the exponent we want. When n equals 2, you'll get 2 times 2 plus 1, which is 5. So that seems to be matching perfectly. So then on the bottom, we're going to have 2n plus 1 factorial, just matching what the pattern was in the factorials. And there we have it. There's a Maclaurin series, a series that was generated by this definition of the Maclaurin series for sine x. There it is. So this is equal to sine x, at least wherever it converges. Now, we're not asked to figure out the radius of convergence here, but I'll just let you know it's everywhere, so it turns out to be everywhere. It kind of makes sense because it's not too different from e to the x. The alternating part isn't going to really affect the convergence that much. And so since we have a factorial on the bottom, then this is going to make it converge just like the e to the x converged. Okay, so there it is. There's the Maclaurin series for sine x. Now example 4 says, find the Maclaurin series for cosine x given your result in the previous example. Now one thing to remember is that we said that if we have a power series, then we can take the derivative of that power series term by term. So now that we have a power series expansion for sine x, we can note that the derivative of sine x is cosine x, so the derivative of this power series of sine x will be the power series for cosine x. All right, so let's do that. Here we're just going to write out what sine x, this is what we found before. Sine x is equal to, and we'll write out the expanded version here first. So x minus x cubed over 3 factorial, just writing out what sine x, what we found here. And then plus x to the 5th over 5 factorial. We could write x over 1 factorial as well if we wanted to. Here it's not going to really matter. And then minus x to the 7th over 7 factorial, and so on. So this we can write out using summation notation, just as we did in that boxed form above. So there's the summation notation or sigma notation. So what we're going to do is, to find cosine, take the derivative of sine. That gives you cosine. Now if we take the derivative of the power series version of sine, now I'm using the word power series just in the most general sense of the word series, but technically we found a Maclaurin series, right? That's the specific kind of power series that we found. So if we take the derivative of this Maclaurin series, we're going to have 1, and then plus Here the 3 will multiply in front and cancel off one factor of 3 from the factorial, leaving the rest of the factors, which we can write as 2 factorial, left over. So we'll have, oops, this is minus, we'll have x squared over 2 factorial. So this is the derivative of x cubed over 3 factorial is x squared over 2 factorial. Just think, the 3 multiplies in front, cancels off that first factor of the 3 factorial, and leaves you with a 2 factorial left over. And when you subtract 1 from the exponent, you'll have x squared. Now that same thing is going to happen with the x to the 5th over 5 factorial. That first factor of 5 is going to cancel off. And you'll have an exponent of 4 and a 4 factorial. Then we're going to have x to the 6th over 6 factorial for the same reason. Okay, so there's an expanded version of the power series expansion for cosine, or in other words, the Maclaurin series. That's what the Maclaurin series would look like. So, let's see. What we want to do, edit that part out, is then look at how we would take the derivative using the summation notation version. So remember that the derivative works its way into each of these terms, and really it just applies to the x to the 2n plus 1. So that 2n plus 1 exponent will multiply in front, cancel off the first factor of the factorial, that 2n plus 1 from the factorial. The next factor is 2n, and then you have all the factors down below it going down to 1. So you're going to get a 2n factorial left on the bottom. Let's start writing this out. Negative 1 to the n, and then we've got x to the 2n over, and then 2n factorial. There we go. All right. Now, one thing we had to worry about when we did this before is, did we lose any term? Because maybe we have to start at n equals 1 instead of n equals 0. Well, let's check. Well, the first term here was not a constant, it was x. And so that first term, the n equals 0 term, is still there when after we take the derivative. The derivative of x is 1. So actually we can start off at n equals 0 still. We don't have to write n equals 1 because we didn't have a constant term disappear after when we took the derivative. Okay, so there's the Maclaurin series of cosine x. Great. So example 5 says find the Maclaurin series for x cosine x, given the results from the previous example, from example 4. All these examples are chaining together. Well, 3, 4, and 5 at least. Well, here it's not too bad. It looks like it's scary, but it's actually not that bad at all. We know that the expansion for cosine x is negative 1 to the n times x to the 2n over 2n factorial. That's from example 4. So all we have to do is multiply the x into that power series expansion, to the Maclaurin series. When the x multiplies to every single one of these terms, we can multiply it to the x to the 2n, because you can like multiply it to either this factor or that factor, and might as well put it with the x to the 2n, and you'll get x to the 2n plus 1. So you get the sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n factorial. And that's it. There's the Maclaurin series for x cosine x. So we'll end the video there. Thanks again for watching, and see you in the next one.